Moving on to our next talk, it will be Professor Christopher Morrison or Dr. Christopher Morrison from Ultrasafe Nuclear Technologies. His presentation is on commercial radioisotope solutions for lunar thermal management, watt scale electricity, and X-ray remote sensing. Please take it away, Chris.
Oh, thank you. Jumped in just in time. I was in the Teams meeting and popped over to WebEx. We had some technical challenges. Anyways, I'd like to take a moment to talk to um, all of you. I'm a technologist. I work on technology, and I'm looking for an opportunity to talk to scientists who can potentially use this technology to do great things. And one of those technologies that is very pertinent to the moon is nuclear technology. That, the lunar night is very challenging. The thermal conditions are extremely challenging, as we've just heard from many sessions. And traditionally, we've used plutonium-238 as a technology. It's a great technology, but it has some challenges, mainly that it's plutonium, and there are weapons proliferation challenges. And I mean, if you're a big NASA mission, you can obtain this technology, but if you're a commercial company, you really can't. And for the smaller NASA missions, it's much harder to get in that area. So there are commercial technologies that are not quite as good as plutonium, but they can work pretty well on the moon. If you want to go to Pluto, use the plutonium. But if you want to go to the moon, it's a lot closer. It's a lot easier. Next slide. Or do I have slide control? There you go. So my company does a lot of nuclear technology. We recently got a big contract for nuclear thermal propulsion with NASA's program. We're doing well, but what I'm here to talk to you today about is specifically the nuclear battery technology. Next slide. So I mentioned, plutonium-238 is great, but there's a lot of other options. In particular, options with shorter half-lives. And the moon isn't that far away, so you don't need that 90-year half-life to do great science on the moon. Half-lives as short as even just a few months could enable your mission. So what we've looked at, there are two isotopes that I've circled there, and these are commercial isotopes. They're commonly used in the medical and they can be produced in much greater quantity. So we have a technology that we've been working with that focuses on the supply chain. How can we produce this? And it focuses on the regulatory pieces, because launching it into space isn't necessarily easy when you have something that's radioactive, putting it in space. What if there's a launch accident? The good news is the plutonium-238 program has blazed that trail. But there's challenges associated with it, but we think, this is a technology whose time has come. Next slide. So I'd like to introduce to you what I would consider our minimum viable product. And this is something we've been working on as a 10-watt thermal lunar heater. We use these small cab units that are shown there. In the center of the units is a precursor. And on the outside is an encapsulation material. And what we do is we put these units in the bottom left diagram. You can see we manufacture them. When we manufacture them, they're not radioactive, but then we put them into a nuclear reactor and charge them. That's where the name chargeable atomic battery comes from. Once they come out of the reactor, they're hot. So we put them in a hot cell and package them into a device that can shield it and properly maintain it. And in the top right, again, you can kind of see that we have something that's a cab stack that puts one or more of these units together, and then ultimately it's assembled into a shielded and aeroshelled device to survive any type of launch accident scenario. The size of this is roughly the size of a softball, and it can provide 10 watts of heat for on the order of multiple lunar nights. After a few years, it does decay. It's not plutonium. But this technology that we're working on with thulium, that's just one of the radioisotopes. So we have longer-lived radioisotopes, shorter-lived radioisotopes that can all be. So cobalt has a 5-year half-life. We have a europium one with a 13-year half-life. And we are currently working on a TRL-6 plan for 2023. As I said, a lot of this technology is based on the medical industry. So taking those innovations from the medical industry and bringing it to space is fairly straightforward. The regulatory challenges are formidable, but because of the way we've approached our safety systems with encapsulation, going with liners, going with sealing systems, this is a defense in depth approach that considers any type of accident that could happen on a launch vehicle. And you know, the fundamental thing here is this is a real technology, and back in the 1960s, NASA actually looked at many of these radioisotopes, but they chose plutonium because it's the best technology. But when we're looking at the Artemis program and a lot of things coming up, we think we have something that's really effective. But next slide. Some of the things we need to do is vet with you, the potential customers and scientists. Hey, is this useful? If you could have 10 watts on the moon and survive with that heat, would that be useful to you? So this is kind of what I would call a vignette that shows, hey, using a traditional battery to survive the lunar night, we can get a 5 to 10 times mass decrement over that. And in terms of volume, this is extremely compact. It's a very small sized technology. Next slide. And something that I would love to do is I am not really a scientist. I'm an engineer, as I said, and there's been a lot of really cool things that the scientists have done. Especially, one of the examples I picked is the MUR program had the AXPS instrument, which had a very low curium source in it. And what we could do is we could easily make a much greater source of X-rays than that. This is a technology where it could be used for heat or electricity, but we can actually use the radiation effects. And as our isotope decays, it creates bremsstrahlung, typically as a beta decay. And that bremsstrahlung can be used in combination with X-ray backscatter to actually get an in-depth view of this, up to a few centimeters into the potential lunar regolith. So the idea is here you have a rover, and instead of needing to drill a bunch of holes, you just drive the rover over regolith and you get kind of maybe a couple to several centimeters into the surface, and you analyze the backscatter of the X-rays, and you can kind of infer, hey, hydrogen has less backscatter than heavier molecules. So if you combine it with a physics model, you might combine it with other wavelengths of light, and you can get a really decent picture of what's in the soil. Next slide. So, these are just a few of the ideas that we have. Heaters, electric power. I know a lot of people talk about the gravitational wave observatories or various other, there's a lot of scientists we've talked to that say, hey, 100 watts on the moon would be enabling, but it's really hard to get an RTG. So we're looking at solving that as a potential commercial solution. It will be heavier than MMRTG, but it could allow that type of power ranges. If you're looking at ISRU, this is just a hot rock. Depending on how we build it, is at least compatible to 1800 Kelvin and potentially up to 2500. So if you have maybe a prototype plant where you want to demonstrate something even up to the melting temperature of lunar regolith, that could be a thing. So anyways, we're looking for partners and friends, and if this interests you, please reach out to me. I'd love to chat.